My name is Brad Nelson. I'm a professor here at the ETH Zurich, professor of robotics and intelligent systems, and my specialty is combining robotics with micro and nanotechnologies. In the Institute of Robotics and Intelligent Systems, I run the multi-scale robotics lab, and so our goal is to understand how we can build intelligent machines that operate from micro to nano scales. So we do a lot of design of these machines, fabrication of these machines, testing of these kinds of machines, these nano machines and micro machines, and then we try to find applications for them in the real world. So, a lot of the applications we find are in biology and medicine. So if we can make tiny little things that can move in intelligent ways, one of the obvious applications would be in, for instance, small devices that carry drugs that could target a particular location in the body to deliver drugs. We do a lot of work in the eye and work on how we can deliver drugs to the retina at very specific locations. But we're also interested in fundamentally how do we make small things and things smaller than a millimeter all the way down to a nanometer in scale. How can we make those small things and make them move in controlled and intelligent ways? A lot of the processes are derived from the semiconductor industry, the same industry that makes computer chips for your smartphones and your laptops and your computers. We use those same kind of manufacturing processes to make mechanical devices of a similar scale. A lot of our inspirations come from bacteria that have these small rotary motors. So some bacteria like E. coli and Salmonella have evolved rotary motors that are around 45 or 50 nanometers in diameter. While we're not at the point where we can make motors that small, what we can do though is look at the physics of why do they have rotary motors. They have these little flagella that turn like little propellers and propel itself in their environments. And so we look at that, we're inspired by those kinds of organisms we see, and then we try to understand how can we use some of these fabrication processes that we borrowed from the semiconductor industry to make devices that move like an E. coli or a Salmonella bacteria. One of the things we started to look at recently, for instance, have been in environmental cleanup, where these devices may be able to go and help catalyze certain pollutants and help clean up the environment. So we're looking at different kinds of applications where we can send out swarms of these, hundreds, thousands, millions of these devices to try to clean up polluted streams and things like that. But a lot of the work is very fundamental, just how do we control these small things? And then as we do that, we start learning things and find applications. And so even along the way, applications come up that we didn't envision. For instance, one of the techniques that we've patented has been a particular way we can generate magnetic fields to control small things. Now, that patent that ETH owns now has been licensed by a company. They're not interested in controlling micro-robots with it, but they're using it to guide catheters that are going into your body, for instance, into the heart. And so a lot of these technologies, as you're going down this path, they spin off into areas that we really didn't originally consider. I've been at ETH 12 years now, and I've seen this field change in just the past decade. So the next decade, I'm excited to see what's going to happen. I think that we will see devices that are able to be controlled and that will be able to do targeted therapies, for instance, delivering drugs to very specific locations in the body, perhaps delivering stem cells to locations to help treat things. So I see some of those applications certainly in a 10-year time frame. But it's more than just solving technological hurdles and solving the engineering and science. We also have to work closely with medical doctors to understand what the needs are there. And we also, to get these into the clinic to really help people requires a tremendous investment. And so then we also have to have business people. We have to have business models that make sense for this to go that far. So it really brings together not just the engineering and science, it also brings together medicine. And even you've got to consider the business side of things. And does this make sense from an economic viewpoint to push the technology in these directions? So.